Hello and welcome to another live stream of Chemistry 223. My name is Travis and I'll be working with you today. And today we're going to talk a lot about galvanic cells, voltage potentials, and other fun things like that. Mainly chapter 17 from your textbook OpenStax. First, I want to post a few links in the chat window here. These are links to the Learning Center's webpage as well as their Facebook and Instagram. Follow them on Facebook and Instagram to get updates on any new resources they have. And I'll also post a link to the Portland State YouTube channel. This is specifically a playlist for all the videos I make for this class. And you can also find playlists for previous classes through the YouTube or PSU Learning Center's YouTube channel. As always, you can drop by my drop-in tutoring hours right after this live stream on Saturdays until 5 p.m. That's in the Pingy app. Just look for chemistry drop-in and you should be able to find me there, or chemistry 223 drop-in hours. And I'm usually there up until 5 o'clock right after this stream. So let's get started today. This first question is asking us to balance the equations below, assuming they occur in, let's go back to this one. Assuming they occur in an acidic solution. There's a slight difference on how you balance these. It's mostly the same process, whether it's acidic or basic. Just at the end of the day, if it's basic, we want to cancel out those H pluses with OH minuses. So in this case, we're doing an acidic solution. So let's get started here. So what you want to do here is break these up into the half reactions that are occurring in those and go through a few basic steps. So first, I want to break it up between H2O2 and H2O, as well as SN2 plus and SN4 plus. So I'm going to start out by writing SN2 plus on one side and say that's producing SN4 plus. The other side of the equation, the other half of the equation, is H2O2 is producing H2O. So the first step is to balance the equation. So you have the right number of atoms on either side of that equation, but you ignore hydrogen and oxygen because we're going to deal with those in later steps. So on both of these, they're already balanced. You see on the right one, this peroxide and water isn't really balanced, but it's all hydrogens and oxygen, so we're not going to worry about it. This one here, which is strontium, is already balanced. It's just the charge is different. So we'll deal with that in a second. The next step to it is to add in oxygens to make sure the oxygens are balanced. In this case, the right-hand side of the equation, we want to basically double that H2O, right? Because we have two oxygens as the reactant, and we want to have two oxygens as the product there as well. So that balances the oxygens, doesn't balance the hydrogens yet, but that's going to be the next step, is to balance those hydrogens that we need. And to do that, we need to add two hydrogens to the left side. Because we already have 4 hydrogens over here, we need to have 4 hydrogens on this side too. So I can say plus 2H plus, and that's still going to be producing 2H2O. So now we have a balanced atoms on either side of both of these two equations, both of those half reaction equations. But we need to balance the charge, which is the next step for it all. We can see over here we have strontium 2 plus and strontium 4 plus, and we balance the charge by adding electrons to one side, so we get a balance of charge. So in this case, the more positive side we need to add electrons to. We would add 2 electrons. Each of those are -1. I have a -1 charge to each of them. So that should give us a net charge on both sides of that equation, which are equal to each other, of 2 plus. Looking at the peroxide and water half reaction, we need to make sure we add 2 electrons to the same side we added those hydrogens. Because those hydrogen ions basically gave it a 2 plus charge, and we needed to give a 2 minus charge as well to keep it neutral. So now we have this balanced half reactions on both sides of them. We can combine those half reactions together. So I'm just going to write out the products, or sorry, the reactants of both of them, producing then the products of both of them. So that we can say that's H2O2 plus SN2 plus 2H plus 2E minus. So that's all of the products kind of from here, or sorry, all the reactants from there and from there. And then I'm going to add all the products to that. So that would be H, in this case, 2H2O plus SN4 plus 2E minus. And those were all the products that we had. And now we can cancel out anything. If you did everything right, your electrons should cancel out. If you don't have the same moles of electrons here as here, we would need to multiply one side of the equation, or one of those half reactions, to match the other ones. In this case, we have the same, so we're not going to worry about that. We'll see an example of that later on. And now we can rewrite that equation out as the net reaction is producing 2H2O plus SN4 plus. And we can see we have a balance of charge and we have a balance of matter. So those are the two things we're looking at. We want to make sure we have the same number of atoms on either side of the equation, because we're just moving atoms around within these reactions, and the same number of charge. The net charge should stay the same in both of these. And if we have both of those, we're happy. Oh, happy face. Bam. So that would be the balanced reaction for that one. For part B, we can write it out as PbO2 is producing Pb plus 2, or 2 plus. On one side, the other half reaction would be with mercury, which is Hg. This is Hg2, 2 plus. So first thing to do is to balance those chemical reactions with everything except for hydrogens and oxygens. So on the left-hand side here, the Pb is balanced already, right? We have the same amount of lead in both sides of that reaction. The oxygens we're not going to worry about yet. We'll deal with that in the next step. On the mercuries, we need to add a 2 in front of there. So we have to make sure we have the same number of mercury atoms in both sides of that reaction, or half reaction as it would be. Next, we want to look and actually add enough water to balance those oxygens. So when you're balancing the oxygens, you want to make sure you're adding H2O to that, and that's where that oxygen is going to come from. And that's why we do that step before the hydrogens, because then we add hydrogens to balance the excess hydrogens from the water. So in this step, blue, we have PbO2 producing Pb2 plus, and I want 2H2O. And I want that 2 because I need the 2 oxygens from that to balance out the oxygens from the lead dioxide, the lead 2 oxide. And now we can go through the next step, which is to balance those hydrogens. To balance the hydrogens on here, we would need to add enough hydrogens to keep it balanced on both sides. So in this case, we see 4 hydrogens right here, 2 times the 2 from water. So we need to add 4 hydrogens to the left side as well. It'll be PbO2 plus 4H plus produces Pb2 plus 2H2O. On the right hand side, we're happy. That's perfectly balanced except for charge. And so the next step is to now balance charge on both of these. We can see on the right side, we go from a neutral charge to a +2 charge. So we need to neutralize that +2 by adding 2 electrons. Now we have a balance of charge and a balance of matter on that one. On the left side, we need to balance the charge as well. To do that, we added 4 hydrogen ions, little protons in there. We need to add, an equal number of electrons. And we'll see that that then produces Pb2 plus. Oh, you know what? I'm sorry. We don't need to add the same number because we have a positive charge Pb. We need to add 2 electrons. By adding 2 electrons, we get the net charge on both sides to be a positive 2, which is what we're looking for. There we go. Now that we have the matter and the charge balanced on both sides of both of these half reactions, we can combine them together to get what the actual balanced chemical reaction is going to be. So writing that out, it would be PbO2 plus, I'm going to do all this in a nice purple color so it's distinctly different than the rest, plus 2Hg plus 4H plus 2 electrons produces Pb2 plus Hg2 2 plus 2 electrons. And inevitably, if you don't have to multiply everything, or once you get to this balanced reaction, your electrons should be canceling out on both sides. We're moving electrons around in this reaction, but we never produce them. They always get absorbed or kind of moved around from another one. Now we can write out the balanced reaction. The final would just be O2 plus 2Hg plus 4H plus is producing Pb2 plus Hg2 2 plus. And there you go. So that would be our final balanced chemical reaction here. Same with up here. And notice in both of these, we have extra hydrogen ions floating around in there. That's the acidic conditions that we're talking about. If this was basic, we would have to neutralize those because there would be an additional reaction with OH minus or hydroxides floating around in solution. Part C has aluminum, so that's Al, and that's going to turn into Al plus 3. And the other side was chromate, Cr2O7. Oh, that's chromate. It's chromium something. That was a 2 minus, I believe. Yeah. And it's producing just Cr plus 3, or 3 plus. So again, the first state is to make sure we have the balanced atoms on there. For aluminum, we have 1 mole of aluminum on either side. We're happy there. Looking at the chromium, we have 2 on the left side and 1 on the right side, so we have to add an extra 2 in there. After that, we want to balance those oxygens. So to balance the oxygens on the chromate or chromium half reaction, that Cr2O7 2 minus is producing 2 Cr3 plus, and we need to make sure we have 7 oxygens. So we have to add 7 H2O to that. And I'll turn what I'm changing into red. There we go. So we're adding 7 moles of water for every chromium that we have, just to keep that balanced. Now we have to go through and balance the hydrogens. In doing that, we would have Cr2O7 2 plus. That should be a plus, I believe. No, I have it as a minus. Oh yeah, the whole thing's minus. And it's producing, in this case, 2 Cr3 plus 7 H2O. But like I said, we need to add enough hydrogens to balance it, and we add them to the left side in this case. So that would be plus 14 H plus. That's hydrogen ions. We have to add 14 because we have 7 here, but it's H2O. So we multiply those two numbers together to get 14. Now we have a balance of hydrogen in the reaction. So now we have to look at charge. For charge on the left side, we have a net charge over here of a plus 12. On the right side over here, we have a plus 3 times 2 is plus 6. So we need an additional minus 6 on this side to get it down, because we can't add any more hydrogens over here. So we have to basically add electrons onto the left side of that equation to reduce the charge. So that'd be CR2O7 2 minus plus 14H plus a 6 electrons would do it, bring us down to a net charge of plus 6 on every side. There we go. And the aluminum, we have to balance that charge as well. To balance this one, all we really have to do is add 3 electrons. Now, we added 3 electrons to the aluminum, and we're adding 6 electrons to that chromium half equation. So to get this to write it as a balanced equation so we can cancel out those electrons, we need to take this whole thing and multiply it times 2. Then we could write it as a balanced equation and cancel out the electrons. So let's do that. So that's 2 aluminum plus Cr2O7 2 minus plus 14H plus 6 electrons is going to produce 2 aluminum 3 plus 2 chromium 3 plus 7H2O plus 6 electrons. Again, we have to multiply each of these by 2. See, I did that there, and there. Now the electrons will cancel out smoothly, and we have a balanced chemical equation, which is 2Al plus Cr2O7 2 minus plus 14H plus is producing 2Al 3 plus 2Cr3 plus 7H2O, and there we are. So those are the stages for balancing the acidic reactions and these half reactions. Basically, write out your 2 half reactions, balance everything but oxygen and hydrogen, then balance the oxygens by adding H2O to make up for the extra oxygens you need. Then you can balance the hydrogens just by adding H plus ions in an acidic solution. Then you balance the charge after that with adding electrons to either side to make sure it's right, and then you can combine them together, making sure that you multiply one side or the other by some number to get the same number of electrons in your products and your reactants, so you can cancel those out. Number 6 is in basic solution, but it's the same idea. We're only going to do 2 of these because it's really the same idea. But there's one last step at the end, which is to basically neutralize the H plus ions by adding enough OH to turn it all into water. And we'll see that here in a second. So this first one is SO3 2 minus, and that is basically turning into SO4 2 minus. And the other reaction here is Cu OH2 is turning into CuOH. So the first step is to make sure we have the right number of atoms on either side, ignoring oxygens and hydrogens. In this case, we have one sulfur on each side, so we're happy there. We have 1 copper on each side, so we're happy there. So we can just kind of move on from there. And then now we have to try to balance those oxygens by adding water. So on the left one here, we have 3 oxygens and 4 oxygens, which means we have to add 1 H2O to the product side of that. Nope, I have that wrong. To the reactant side. There we go. The copper hydroxide, in this case it goes from copper 2 to copper 1. We have here 2 oxygens in here and 1 oxygen there, meaning I have to add 1 H2O to that side there. Now we have the right number of oxygens on either side. We have to make sure we're balancing the hydrogens. So writing this out, SO3 2 minus plus H2O, producing SO4 2 minus. On this one, I have 2 hydrogens on the left-hand side. So I need to add 2 more hydrogens to the right. H plus, I forgot my 2 H plus. Now we have a balance of hydrogen ions, or hydrogen on both sides. For the copper, we have 2 hydrogens here, 1 hydrogen here, and then 2 more there. So there's 3 total on this side. There's only 2 here, so we have to add 1 to that reactant side. So this would be CuOH2 plus H plus produces CuOH plus H2O. So now we have a balance of oxygens and hydrogens for both of those two. We want to look at the charge. So for the charge on this guy here, we have a -2 on the reactant side, and we have a net of a -1 on the product side. So we would have to add an electron to the reactant side. And just 1 electron should do it to get us down to the same charge as what we have. Oh, I'm sorry. We want to add an electron to the other side. Yeah. So SO4 2 minus plus 2H plus. So let me get started here. Let me correct myself. Here I have a -2 and a +2, so that's going to be a net of a neutral, a 0 charge. Here I have a -2 charge. So I need to add 2 electrons to the right-hand side. I can't add any more hydrogens because I've already got things balanced, but I can add electrons in there. So I'm going to do +2 electron minus. And now I should have a net charge of -2 for both sides of that. For the copper half reaction over here, we have a net charge of +1 and a neutral charge over here. So I'm going to have to add an electron to the reactant side. There we go. So now we should have a neutral charge on both sides of those half reactions. Now, one thing you might notice is we don't have the right number of electrons on both these. They're not the same. So in this case, we have to take this whole equation and multiply it by 2, just so we get the right balance of electrons on there. So now, writing this whole thing out, I'm going to have SO3 2 minus plus 2 CuOH2 plus H2O plus 2H plus 2E minus. So that's going to produce SO4 2 minus plus 2 CuOH plus 2 H2O plus 2H plus 2E minus. So right away, these 2E minuses cancel out. That means I multiplied things correctly in there. Now I also have this H plus here and here, which are going to cancel out as well. So all my hydrogen ions cancel out. I have water over here, which I have two waters on the right side. So one of the waters will stay on the right, but all the waters in the product or in the reactant side will go away. And now we have our balanced chemical reaction. SO3 2 minus plus 2 CuOH2 is going to produce SO4 2 minus plus 2 CuOH. And if we had any of these H plus hydrogen ions left over, we would have to add OH minus hydroxide ions or hydroxide to balance that in there. Jump over to part B. Part B is a fun one because we start out with O2 on one side and it produces essentially nothing. We don't have anything to balance that O2 with there. I'm going to write the other one, Mn, manganese, OH2 is producing MnO2. So in balancing first everything but oxygen and hydrogen, we see on the left equation, we don't have to balance that yet because it just has that oxygen. On the right one, we can see that the manganese is already balanced, so we can go on and try to balance the oxygens. Now when we balance oxygens, that's when we would add 2 H2O to that left side. And then over here, we have 2 oxygens, and 2 oxygens were already balanced. So then to balance the hydrogens, I would need to add 4 H plus ions to the reactant side over here to get that to be balanced. So now I have 4 hydrogens on each side and 2 oxygens on each side. On the right hand side, I have 4 hydrogens in my reactant here, and I have no hydrogens over here, so I need to add 4 H plus ions. So now I have the right number of hydrogens, the right number of oxygens for both of them. We need to make sure we can balance that charge. The charge over here, 4 hydrogen ions gives it a +4 charge. So we want to add 4 electrons. So now we have a neutral charge on there. On the right, we can see we have a +4 charge on the product side. So we would need to add 4 electrons to that same product side. To make it neutral, because our reactant starts out as neutral here. Same over here, our product was neutral, so we had to make sure both sides were neutral. Now we can write that whole equation out as O2 plus MnOH2. Oh, I should note that since we have the same moles of electrons on either side, we don't have to multiply it by any type of factor. So that plus 4H plus 4E minus produces MnO2 plus 2H2O plus 4H plus 4E minus. Balancing these out, the electrons go away, the hydrogen ions go away, and we're left with a balanced reaction of O2 plus MnOH2 produces MnO2 plus 2H2O. And again, since there's no hydrogen ions in there, it could work in a basic solution. The key to the basic solutions is making sure that all of your hydrogen ions get canceled out. And if they don't, you need to add OH minus. In this case, they did, so there was no worries. Move on to number 11. This is talking about cell reactions and writing the cell notation for these cell reactions. So in the in galvanic cells and I don't know how to say that word. In galvanic cells or other type of electrolytic cells, we have basically two electrodes in two different beakers with a solution in there, ionic solution, and then a salt bridge between them. And we can figure out the oxidation and reduction reactions that are happening with both of those electrodes or the solution that's in there, and then write them out as a certain type of notation. In this case, we call it cell notation. I'm going to try to generalize this by kind of saying the anode, we put a little bar, and this is the anode ion, or whatever ion is in the solution for the anode. And we put a double bar there to represent kind of that salt bridge separating the anode from the cathode. And then we put a cathode ion. And you'll sometimes see those ions represented as concentrations of the solution, so you can actually see what type of solution they are. And we put a bar and then the cathode. And oftentimes those cathodes are actually the cathode electrode. So I could write electrode, cathode and anode. So oftentimes we will use the electrode as the same material as the anode or the cathode ion, just so we're adding material to it or subtracting material from it. But oftentimes, if we don't have that and the anode and cathode ions are just in solution, we can use more of an inert thing like platinum. So you'll see that comment in there. So in these cases, what we want to do is write out the half reactions for those, figure out which one's oxidation and reduction, and then write them out in the cell potential or cell notation that's here. That's where it says use platinum as an inert electrode if needed. So all that said, what we want to find out for part A is what is the oxidation and reduction. Half reactions for these. And the oxidation is going to be the anode, and the reduction will be the cathode. And the way I like to remember it is I focus on the oxidation, and oxidation is always losing its electrons. So when you write out its half reaction, you want to start out kind of whatever's solid in the reactant is a good place to start. If there isn't any, you're looking for things that are going to get more positive between the reactants and the products. So in this case, we have MgS, which is producing Mg2 plus 2 electrons. Just get that balance. And you see the product has 2 electrons in it. That means it's losing those electrons. Therefore, it's an oxidation reaction. If it were to gain those electrons, it'd be a reduction. But when it's losing those electrons, it's an oxidation. So that would mean that the other reaction on here is a reduction reaction. And we can see that here. Oops, that's an M. I want an N, nickel 2 plus, aqueous. Can't write A's and Q's. We want to add to that 2 electrons to keep it neutral because it's forming and becoming nickel solid. So you can see the solid form in this case, and oftentimes you'll see the solid form, but sometimes they're going to be ions on both sides of it. But you'll want to see the change in charge between that same atom, the nickel to nickel from product to reactant, and what's the difference in charge? Is it getting more positive, more negative, more neutral in this case? Since it lost a positive charge, it's gaining those electrons in there, which means that it's a reduction reaction. So we can write this now as I have it up here in the cell notation kind of idea. We start with the anode, and then we work our way into the ions, and then end up at the cathode electrode. So the anode was Mg, solid. Put a bar. And here we just have Mg2 plus. That's our ion. It's aqueous. Double bar. Going to nickel 2 plus. Aqueous ion. into nickel solid. So in this case, we didn't have any inert electrodes. Both of the electrodes were actually turning into a solid form, which means that the solid form is the electrode, most likely. For part B, up here we have 2Ag, which is turning into 2Ag plus ion, turning into 2Ag solid. So I can write that as just Ag plus becoming Ag solid. This is aqueous. So that's silver. And we can see, in this case, I wrote it up at the top, but since it's starting out as an ion and then going down to a solid, we know it has to gain an electron in there. And since it's gaining an electron, it's going to be a reduction reaction. So then the oxidation would be the other one, Cu. And sure enough, it starts as a solid, always a good sign. And it's going to be turning into a Cu 2 plus aqueous, which means it needs to gain or lose 2 electrons in the process. So you can see the difference in oxidation and reduction just by following where those electrons are in the half reactions. If they're in the product, they're going to be an oxidation, and if they're going to be in the reactant, they're going to be a reduction. So now writing out the notation for this, the anode's always the oxidation. Therefore, we have copper solid going into copper 2 plus aqueous solution. Salt bridge going to an Ag plus aqueous solution. Notice the 2 didn't really do anything in this case. Since all we're really worried about is that cell notation, the 2-to-1 ratio of that doesn't really matter. We could put 2's in front here and here, but we wouldn't put a 2 in front here. So that's why I just left out that 2 altogether. And then in this case, it would be a silver solid, which would be our electrode for the cathode. Part C. For part C now, the oxidation half reaction would be going from Mn solid to Mn 2 plus. This NO3 is going to be a negative charge to it. There's 2 of those, so it's got to be that 2 plus. And that would be an aqueous. So since it's a 2 plus, it goes from a neutral to a 2 plus, we have to add to that 2 electrons. And there we go. The reduction reaction would be the other half of that. So it'd be Sn aqueous, Sn 2 plus aqueous. Same idea, we have 2 NO3 balancing it out to make it neutral, turning into Sn solid. So since it goes from a 2 plus to a neutral, this has to have 2 electrons, each electron being a -1 charge. So now we can see our cell notation would have to be Mn solid, Mn 2 plus aqueous, Sn 2 plus aqueous, Sn solid. There you go. So this cell notation is just useful to show kind of like what the what state the electrolytic cell is going to be in, and how to set it up if you wanted to. So you could set up kind of this electrode over here, this electrode over here, and some solution with ions floating in there, and you can have some counter ion as you see fit. Notice it doesn't really mention this NO3 at all, you could use any type of counter ion at that point, as long as it stays in solution as it should. If it precipitates out, then it doesn't work. So yeah. The last one, part D. Part D, it has copper and gold. So the copper is going from, looks like a +1 to a +2. Notice there's 2. So that Cu plus is going to Cu2 plus. So that would have to add to that an electron. And see how it's going from a +1 to a +2. That means that it's losing an electron. So it's going to be our oxidation. Half reaction. The reduction excuse me, would be the gold. Notice the gold is going from a 3+ to a solid, which means since going from a 3+ to a neutral, we're getting 3 electrons. Wrong color. There we go. So this one is where it gets a little interesting. When I write that half reaction, I have to write what the electrode is for the anode. In this case, we have copper, and I didn't write it down here. It's really aqueous. So in all stages, copper is aqueous. It never really solidifies or precipitates out of the solution. It just goes from a +1 to a +2 charge. So we need some type of solid electrode in there to be part of that process. And that's where this platinum comes in. So when using platinum, we just list it as platinum solid is going to be our anode. But our cathode is going to go from copper plus aqueous to copper 2+ aqueous. So really both of those are going to be in that solution, kind of floating around. And it's going to be that reaction in that solution that's happening there. Then we have our salt bridge on the other side, in the other beaker, so to say. We're going to have gold 3+ aqueous. And then that's going to be adding or subtracting to gold solid, depending on the voltage potential between those. And we'll get to that more very shortly, I believe. So that's the general idea between this cell notation and what's going on there. It's useful to know when you see this, kind of just what it means. And breaking this down into those half reactions is a really useful thing to do in determining where those electrons are going to be. Number 18, I got a few more, a lot more. Okay, so let's jump. Yeah, let's do number 18, and then I'll skip one and do number 31. So number 18, and I'm going to skip number 18 and just go to 22. I'm running out of time, and I don't want to go too far over, especially in this wonderful heat. So number 22 is to calculate the standard cell potential. And this is a fairly simple thing. Most of these values are tabulated. It comes down to figuring out the oxidation and reduction reactions, which one's the anode, which one's the cathode, and then looking up on the table what the standard electrode voltage potential is of that reaction. And then we can do the electrolytic cell potential is going to be equal to the potential of the cathode minus the potential of the anode. And just using that equation, we can basically find, so kind of like what the product minus the reactant is in a way. It's kind of, and it's really due to the direction of that voltage potential on why we do it kind of in that direction. And then the key is if that cell potential is greater than 0, we can say it's a spontaneous reaction, which means that reaction is going to happen without giving it any extra electricity. We can actually give it some electricity and force it to happen in a backwards way by just changing that voltage potential between things. But for the most part, we're just looking at, is this reaction going to happen one way or the other? And if we flip it around, it becomes the opposite. And we'll see. So we're going to do part C and part D here. For part C, we want to identify what the oxidation is. In this case, it's in a solid which is producing Na+. And then, of course, it would then have to accompany with an electron. It's going to be aqueous. For the reduction reaction, we can see it'd be lithium here, of course. And lithium starts off as a plus. And then we would need to add 1 electron because it turns into a solid. And that's our reduction side of things. Now, to find out these electric cell potentials of these two half reactions, I would refer to Appendix L in your textbook. I can jump over to that in a minute. There it is. And I've highlighted a bunch of different reactions that I've used now and in the past. And just scrolling through these, I try to highlight the ones I use. There it is. Lithium plus E. Lithium plus an electron is equal to lithium solid. Has a voltage potential of negative 3.04. So I can write this out as the, I know you can't see what I'm writing. I'm just writing down that potential. And I'm going to find it for the anode as well, which was a sodium solid turning into a sodium ion. There it is. Negative 2.71. So that's the general idea between how to look those up. We're just looking for in the appendix what that reaction is. And don't worry about the direction of it going. All of these reactions are written as reductions. None of them are written as oxidations. And it's built into that formula that we were using to kind of flip the oxidations around, which is why we have a negative sign there. So if it was a positive sign, then it would subtract it from it. If it was giving you the opposite oxidation voltage potential, if it was a negative, it would flip that around as well, make it a positive, giving it a oxidation voltage potential. So it's kind of built into that. So don't worry too much that the direction of those balanced half reactions are not going in the direction you would hope. But to find the cell potential now, this just equals the cathode minus the anode. Excuse me. So in this case, that's negative 3.04 minus a negative 2.71. I always put parentheses around my negative numbers, especially when I'm subtracting them. But you can pretty easily see that this negative will distribute in, making it all positive. And since this term here is a negative number that's larger than this term here, we know we're going to have a negative cell potential. Ultimately, that negative cell potential is going to mean it's non-spontaneous. So we can do the math for that real quick. Negative 3.04 minus a negative 2.71. That's equal to a negative 0.33. And these are in volts. All the values on that table were in volts. So, and that's going to be our cell potential. Since it's less than 0, that's non-spontaneous. Going on to part D. Part D has, of course, an oxidation. That reaction is going to be the Ba solid, which is going to form into Ba2 plus 2 electrons. The reduction. So why we spent so much time at the beginning of this working these out. These later problems, they use this idea of these half reactions to do it, but you have to solve for something much deeper into it, and they get even deeper later on. So the reduction is going to be Ca2 plus calcium aqueous plus 2 electrons. Let's keep it balanced because it's forming into a neutral solid. So now we can look up what those values are. You look up on the table just the same. I have already looked those up, so I'm just going to write them out to save a little bit of time. Is equal to negative 1.847 volts, and the cathode is equal to negative 2.868 volts. So the cell potential will be equal then to the cathode, negative 2.868 minus negative 1.847. So I'm going to get a negative 1.021 volts. So there's my cell potential there. Again, it's negative, so it's non-spontaneous. All right, so I'm going to hop over. Last one I'm going to do is these two parts of number 31. These are a little bit more complicated than the ones we were already doing. Actually, I guess that's all I had. So in these, I thought I had one more. Oh yeah, this is good. So we want to calculate the equilibrium constants of that. So we have to do everything we just did, where we have to do the half reactions for these problems, find out the cell potential for them, and then using the equation where the E cell potential is going to be equal to RT over NF ln of K, which is really equal. If you they simplified a lot of these variables. R is a standard constant, as well as T is the temperature, which is usually at room temperature, so it's 25 degrees Celsius or 298.5 Kelvin. And N is the number of moles of your electron, and F is the Faraday constant. So R, T, and F are usually fairly constant values because it's always happening at room temperature, and R and F are always a constant. So they simplified a lot of that down, and then they did a change of base for log to change it from a natural log to a log base 10. And all of that basically results in this equation coming out as 0.0592 volts divided by N log of K. So that's equal to the cell potential. So if we can find out what that cell potential is, and N in this case, N equals the number of moles of electrons. Sometimes I write faster than my brain thinks, or vice versa. So if we are transferring 2 moles of electrons between these reactions, N would be 2, and so on and so forth. And notice that it's key that we change from a natural log to a log base 10. This means that we can easily solve for that constant if we know the cell potential, and you can easily solve for the cell potential if you know the constant. There is, I don't have it up anymore. It's a great table in the textbook. I'm going to find, there it is, real quick. There it is, there. So this little diagram shows you it's a really easy way to go from the cell potential to your Gibbs free energy, the standard free energy, and the equilibrium constant, using those three different equations. So you can go back and forth between them. So if you know any two of those, you should be able to find basically all three, which is really nice. And then it gives you some basic rules behind whether or not things are spontaneous or not, based on the equilibrium constants, the change in standard free energy, and the cell potential. So all of those are really useful things to know. So I definitely recommend reviewing those values there and seeing kind of why they work based on those equations. But we're going to get into this guy now. So the oxidation reaction for part A is, this one's a little bit more complicated because we're going from a compound. We're going from silver chloride. Solid is in equilibrium with silver ions and chloride ions. And to find out what these reactions are, I jumped over to my cell potentials and tried to see what cell potentials do I have. Because to find this equilibrium constant, I need to know what that cell potential is, and to find the cell potentials, I need to have some tabulated value of those cell potentials. So looking up at the top, these first two here are screaming at me I should be using these, because you have silver chloride plus an electron produces silver plus a chloride ion. So this is almost what we have, but it's not quite there yet. And then the top one, we have silver plus. So we have silver ion plus an electron is equal to our silver solid. So we can utilize the two of those values to come out with the value we're really looking for. So for my oxidation in that case, I can switch it around and say Ag solid produces Ag ion aqueous plus an electron, because that was one of the values on that table. I did flip it around a little bit to make it an oxidation, but the cell potential for that, and it would have to be flipped around because it's the anode, is equal to 0.7996 volts. The reduction half reaction is going to be equal to the second half of that, the Ag chloride solid plus an electron is producing, or in equilibrium with, really, solid plus chloride ion. And if we were to balance this chemical reaction out, you'd see these cancel out, and we get exactly what this is saying up here. Get that balanced chemical equation. The electrons would cancel out as well. And we would have a cell potential of the cathode, which would equal 0.22233 volts. Again, those numbers are right here off the top of that table. So now that we have this cell potential, I can use it and plug it into this equation here, where 0.22233 volts is going to be equal to 0.0592 volts. And dividing by n is the number of moles of these electrons. Here we have 1 mole, so we're just dividing by 1. So I don't have to worry about n in this case, times the log of k. So some fancy algebra, it's fancy because I'm on an iPad and I can flip that around, is equal to the log of k. So pulling up the calculator, there it is. I can see that 0.22233 divided by 0.0592 is equal to 3.7. Oh, I did that wrong. My mistake. I forgot to find the cell potential. Whoopsie. Of the cell is going to be equal to 0.22233 volts minus 0.7996 volts. So I actually have to find the cell potential first before I can do it. I don't want to just use the cathode potential. So doing that, minus 0.7996. That's equal to 0.577 volts. So 7727 volts. And I can take that value, divide it by the 0.0592 volts, which is going to equal log of K. Oh, this was a negative. Divide by 0.0592. So that's a negative 9.75. Is equal to log of K. Now, to solve for that constant, I really just have to take 10 to the power of negative 9.75 is equal to 10 to the power of log base 10 of K. This says that then K is equal to 10 to the power of this guy. And we have 1.77 times 10 to the negative 10. That's going to be our constant value. So it's an easy manipulation of this value. And don't let the craziness of this all fool you. Just writing this down to say the cell potential is equal to that saves you a lot of headache, because you don't have to worry about what the Faraday constant is or the R constant. As long as you are at room temperature, that's 298.15 Kelvin or 25 degrees Celsius. You should be fine using that equation. If you're at a different temperature, then you got to plug all these values in here. Doing part B on this one is the same basic idea. There's one little trick to it, and we'll run into that. See if I can make a little bit of extra room. That'll do it. So the oxidation. So again, part C is what I'm doing next. I liked part C. So that's oxidation reaction. This one's going to get a little complicated. Looking back at our appendix for mercury reactions, we have this one here, which matches that compound that we have in there, that mercury tetrabromide. And you can see, flipping back, that's the product of what we have, mercury tetrabromide, to a 2 minus. But it's producing, in this case, mercury liquid, in this case, because that's the natural form of mercury, but it's neutral mercury plus 4 bromide ions. So we also have to use this one that's 3 up here, which is mercury 2 plus 2 electrons produces mercury liquid. So utilizing those two as our oxidation and reduction reactions, we can use that to solve for these. And we'll see how we get this net ionic compound here. So if I have Hg liquid plus 4Br minus aqueous produces HgBr4 2 minus aqueous, and that's plus 2 electrons. So I actually flipped that around from how it's on the table because it's an oxidation, and the value they had for that cell potential of the anode is equal to 0.21 volts. So for the reduction, that reaction is going to be Hg2 plus aqueous is producing Hg liquid. So producing liquid mercury, which is the standard mercury at room temperature. Mercury is the only liquid metal, so it's really cool and fun to play with. Although it's also very toxic, so don't play with it. But there's some fun videos of people floating an anvil in mercury and stuff like that, and they use it to stabilize vibrations on a lot of sensitive equipment. So the cathode, that reaction had a cell potential of 0.851 volts. So we can see that our cell potential is going to be equal to 0.851 minus 0.21, which is equal to 0.641 volts. And now they have that 0.641 volts. That's going to be equal to 0.0592 volts divided by N. In this case, I left it off my reduction. There should be a plus 2E minus there. The moles of electrons are 2 in each of those. So I'm going to have a 2 down there for N times the log of K. So if I take this value here and I multiply it by the reciprocal, so that's going to be 2 divided by 0.0592, I get this value here, 2.17. Or 21 is what I want to say, 21.65, let's say, 66. So this is going to equal 21.66. Oops, not equal. Is equal to log of K. So then, put this over here. If I take each of those 10 to the power of, I can say K is equal to 10 to the power 21.66, which is equal to 4.52 times 10 to the 21st power. There you go. So that's a way to utilize that equation to solve for that. And that works at equilibrium. If you're not at equilibrium, you have to use something called the Nernst equation, which is really just replacing that K constant with Q. And Q is kind of the state of equilibrium that you're at. And then you can subtract the standard cell potential from it. And you should get that. Subtract that from the standard cell potential to get what your potential is at that moment. Either way, that's all I have for you. I went a little over time, but I want to make sure I got through at least that much of this chapter. Best of luck for you guys for the rest of the week, and I will see you again on Tuesday.